All right, question number 2. Where we last left Phil, he was traveling 3 meters per second. But now that Phil is traveling 3 meters per second, we're going to say that he slams on his brakes and tries to stop. He and his bike still have the same mass of 120 kilograms. We want to know how far does Phil travel while stopping, right? So if you've ever ridden your bike and you slammed on the brakes, sometimes you skid a little bit of a distance. So we want to know how far is he going to skid if he applies a net force of 20 newtons, right, in order to slow him down. So just like before, I've drawn my before and my after diagrams here. I've got him moving initially, and then afterwards I do have him at rest, right, because he is going to be coming to a complete stop. Just like before, I've listed off all of these possible variables that we could use in order to solve for any missing pieces that we have. So we could look for his mass, his velocity, his momentum, and his kinetic energy, both before and after the interaction. Okay? And then we do also have a little space down here for the during, so we can figure out exactly what's happening as he's sliding to a stop. Okay? So he's traveling 3 meters per second. So I'm going to include that here, 3 meters per second. He slams on his brake and tries to stop, so his final velocity is 0 meters per second. His mass is still 120. Again, I'm assuming that's not going to change before or after the interaction. And we want to know how far does he travel while stopping if the net force on the bike is 200 newtons. So I've drawn my free body diagram. You'll notice that I have my force going in the opposite direction of motion, and that should make sense because if he's moving and he comes to a stop, that means that he has to feel some sort of net force that cancels out his motion or counteracts his motion. So I'm going to include net force here, 200 newtons. Okay. All right. So the first thing we want to know is how far does he stop? Again, we have a couple of equations that deal with distance. The one that we're going to focus on now is this one from our most recent unit, where we know that the work, recall that work is just a change in energy. Okay. The work is equal to the net force that the object experiences and the distance that that force is applied. So we have the net force. We are looking for distance, but if we could figure out the work or the change in energy from the initial to the final motion, then we can solve for our missing distance. Okay? So just like with last time, work is a change in mechanical energy. We're going to look at change in kinetic energy because we have the variables for kinetic, right? Mass and velocity, both before and after. So if I can figure out the initial kinetic energy, we have 1/2 times mass times the velocity squared. We should get 540 joules. Okay, and then finally, when he comes to a complete stop, right? If his velocity is 0, then that means he has no kinetic energy at all. So that's pretty easy to solve for. We have no kinetic energy if we're not moving. So the work done in this case, the change from our initial kinetic energy to our final, well, that is equal to 540 joules, right? That's the difference between 540 and 0. So that's the amount of work that's been done. So now that we know the work, we have the force that's been applied, we can figure out the distance. Okay, how far does it come to a stop? So I'll just plug in the work, which was equal to 540 joules, and that's equal to our net force, which was 200 newtons, and multiply that by whatever our distance is. So now we just have to figure out, well, what times 200 gives us 540? So if we divide both sides by 200, so 540 divided by 200, okay, I'm getting 2.7. 2.7. And because this is distance, that'll be in meters. Okay, so that's how far he's going to skid to a stop if he's initially traveling at 3 meters per second and there's a net force of 200 newtons. Okay, so 2.7 is going to be our distance. 2.7 meters is the distance that's changed. Okay. So before we look at the next question, when we're looking at the stopping distance, okay, you can imagine what's going to happen to that distance if we applied a smaller force, right? So if you're moving and you apply a smaller force, you're going to skid a little bit further until you come to that stop, right? So this basically tells us that the larger the force, okay, the smaller distance is needed to stop, whereas the smaller the force, you're going to need a lot more distance for that object to come to a complete stop, a lot more distance in order to bring that change from your initial kinetic energy down to zero. Okay. All right, so our next question wants to know how far would Phil travel if his bike was originally traveling at 6 meters per second? Okay, so we're doubling our speed. And you've probably known this if you've ever taken driver's ed. The faster you're going, the further you're going to skid to a stop. Okay, so what we could do is we could just, substitute our before with, instead of 3 meters per second, go to 6 meters per second and just do all this math all over again. Or again, we can think about this a little bit more conceptually. Okay, we know that our stopping distance is equivalent to how much work has been done, or how much work we need in order to go from our initial kinetic energy to zero. Okay, we're going from some amount of kinetic energy to zero, and if we can figure out what our starting kinetic energy is, we'd be able to figure out the work pretty simply. Recall, though, that kinetic energy has a very special relationship with mass and velocity. Okay, because this velocity value is squared. Recall that when you double your velocity, you end up you end up quadrupling the amount of kinetic energy. So let me say that again. When you double your velocity, you end up quadrupling the amount of kinetic energy that you have, because this velocity value is squared. So if we were originally at 3 meters per second and we produced 540 joules, if I want to figure out what is the kinetic energy at 6 meters per second, right, I'm just going to quadruple that kinetic energy value. Okay, so 540 times 4, right, quadrupled, that equals 2,160 joules. 2,160 joules. That would be the new kinetic energy if we doubled our speed. Okay, so you can imagine what that amount of kinetic energy is going to do to our stopping distance, right? So if we had a change in energy of 2,160 joules, right? That was the work. That's the difference between our initial and our final kinetic energy. We're still applying 200 newtons of force to slow this thing down. Okay, so what that ends up doing to our distance is that actually quadruples the amount of distance that we're going to need. So 2,160 divided by 200, okay, that equals 10.8. So 10.8 meters is needed for that stopping distance. Okay, and then if we're looking at the difference between these two values, okay, you'll notice that 10.8 is going to be 4 times larger than 2.7, right? 2.7 times 4 gives us 10.8. Okay, so let this be a lesson to speeding as well, right? When you double your speed, okay, if you're going from like 30 miles an hour to 60 miles an hour, you end up quadrupling the amount of stopping distance you would need to come to a complete stop, right? So this does have some implications for driving in everyday situations as well. So we're going to put a couple more videos on for the next two problems. And as always, let us know if you have any questions.